Okay, so next we go into 27.5. So the Compton effect. So at the end of the lesson, the student should be able to define the momentum of the photon in relation with the quantum energy. And then number 2, describe briefly on Compton effect in terms of conservation of energy and momentum. Okay, so photons always travel at the speed of light. Okay, so it means that here, so the speed of photon basically is equal to speed of light, 3 times 10 to the power of 8 meter per second. So what does this tell us about their mass and momentum? Okay, so the total energy can be written as energy square root of 1 minus b square divided by c square is equal to m naught c square. Okay, since the left side, this one, the left side of the equation must be 0, okay, for the photon. So why 0? Because when your speed of photon is equal to speed of light, so automatic this one become 1. So 1 minus 1 becomes 0, automatic this side become, the left side become 0. So it follows the right side must be 0 as well. Okay, of course, if this one is 0, so this one must be 0 also. Okay, so rest mass of a photon, so m naught here must equal to 0. So the rest mass is 0 when v here is equal to c. So when the speed of photon is equal to speed of light. Okay, so the momentum of the photon can be written as p square of 1 minus b square divided by c square is equal to m naught v. So dividing the momentum by the energy and substituting, so we can find that momentum is equal to E divided by C. So it means that here, so this one is a momentum formula. Okay, and this one is the energy formula. Okay, so here when momentum, this formula divide by the energy formula. Okay, so automatic final answer you can find that P here is equal to E divided by C. So finally we can write the momentum of a photon in the following way. So momentum of the photon E is equal to HF divided by C, or is equal to H divided by lambda. Okay, so basically from this formula, E is equal to E divided by C. So E is equal to HF. Okay, so HF divided by C, and then you know that here. Okay, let's say here when you substitute here C is equal to F lambda inside this one, and this one automatically become F lambda. So F and F we can cancel out, and finally the formula become momentum is equal to Planck constant divided by lambda. So Compton directed a beam of X-rays toward a block of graphite. Okay, so Arthur Hurley Compton found that the scattered X-ray had a slightly longer wavelength than the incident X-rays. Okay, so this means they also had less energy. Okay, so the amount of energy reduction depended on the angle at which the X-ray were scattered. So the change in wavelength is called the quantum shift. Okay. Okay, so this one is a diagram of what is one is the Compton effect diagram. Okay, so the Compton assume the photons acted like other particle in collision. Okay, this one like a momentum collision. Okay, remember that one. So energy and momentum were conserved. Okay, So the shift in wavelength is delta lambda is equal to lambda minus lambda naught is equal to h divided by me. Me is the mass of electron time with the speed of light. Okay, so time with the 1 minus cos theta. Okay, so lambda minus lambda phi, this one we call it as a, what is this one, is a change in the wavelength. So we call it as a Compton shift. Okay, so this one here, okay, so your initial, okay, so f naught lambda naught, okay, and then this one going to collision. So this one become f prime here, and this one you have the lambda prime, and then this one should be your theta, but this one should be your e. Okay, indicate that here this one should be your the scattered photon having lost energy, has a longer wavelength and lower frequency than the incident photon. Okay, whereas for this one, the electron recoils just as if struck by a classical particle. Okay, so the quantity h over me times with the c, we call it as a Compton wavelength. Okay, so Compton wavelength here is equal to, the value here is equal to 0.00243 nanometer. So this value you can calculate by using this formula. So this one is a constant value, 6.63 times 10 to the power of negative 34. Okay, and then this one is a mass of electron. So the mass of electron should be 9.11. Okay, times 10 to the power of negative 31. And here should be the speed of light, 3 times 10 to the power of 8 meter per second. When you calculate here, automatically your Compton wavelength becomes 0.00243 nanometer. So very small compared to the visible light. Okay, visible light, so the value basically is equal to, it's around 400 to the 700 nanometer, right? So basically this Compton wavelength should be small, okay, shorter compared to the visible light wavelength. So the Compton shift depends on the scattering angle and not on the wavelength. So experiment confirm the result of Compton scattering and strongly support the photon concept. Okay, so next we go into the 27.6 is the dual nature of light and matter. So at the end of the lesson, the student should be able to state the de Broglie hypothesis and explain the dual nature of light and the matter. Again, number 2, apply the de Broglie wavelength to a particle formula. Okay, photons and the electromagnetic wave. So light has a dual nature. So it exhibits both wave and the particle characteristic. Okay, it depends on the situation lah. Okay, so applies to all electromagnetic radiation. So different frequencies allow one or the other characteristics to be more easily observed. So the photoelectric effect and the Compton scattering offer evidence for the practical nature of light. So when light and the matter interact, okay, so light behaves as if were composed of the particle. And then interference and diffraction offer evidence of the wave nature of light. Okay, so means that here this one situation of the photoelectric effect and this one is the Compton scattering. Okay, so indicate that the light as a particle, and then interference and diffraction indicate the light as a wave. So wave property of particles. So in 1924, Louis de Broglie postulated that because photons have wave and particle characteristics, so perhaps all forms of matter have both properties. Okay, so furthermore, the frequency and the wavelength of the matter wave can be determined. So the de Broglie wavelength of the particle of the mass m and the speed v is lambda is equal to h over p, where lambda is the wavelength, h is the Planck constant, p is the momentum. Okay, you can and then the formula can become h is equal to mv. So here is a momentum formula, it should be mv. Okay, so the de Broglie also proposed that the frequency of the wave associated with the particle obey the Einstein relationship. So Einstein is a relationship, E is equal to hf. If you want to find the frequency, f is equal to E divided by h. Okay, so means that here this one is due to the wave, okay, for wave formula, and this one is due to the particle. Okay, so the dual nature of matter. So the de Broglie equation shows the dual nature of matter. So each contain matter concept, so energy and the momentum mv. So each contain the wave concept. So this one is the lambda and the frequency. Okay, now we go into the example 27.4. The question here, compare the de Broglie wavelength for an electron. ME is equal to 9.11 times 10 to the power of negative 31 kg. Okay, moving at a speed equal to 1 times 10 to the power of 7 meter per second. So with that of the baseball of mass 0.145 kg, so pitch at 45 meter per second. So now we want to find the de Broglie wavelength. Okay, so you can use the formula de Broglie wavelength. Okay, where is the de Broglie wavelength? So this formula, lambda is equal to h over p. So it's equal to h over mv.
Okay, so here example, let's discuss example 27.4. So the question, compare de Broglie wavelength for an electron moving at a speed equal to 1 times 10 to the power of 7 meter per second. So means that here you are given ME here equal to 9.11 times 10 to the power of negative 31 kg. And you are given the speed here is 1 times 10 to the power of 7 meter per second. Okay, so this one is based on the electron. Next one, you are given the mass here, mass of baseball is equal to 0.145 kg, and the speed of baseball here, okay, so is equal to 45 meter per second. So this one is due to baseball. Now we want to compare the de Broglie wavelength, okay, between electron and baseball. So you can go into the formula here. Okay, going back to the formula of de Broglie wavelength, the formula should be lambda is equal to h over p. So here h equal to mv. So in this example, you are given the m and the v here. So that's why you need to use this formula. Okay, this one is a momentum is equal to mv. So automatically it become, for electron, it become h is equal to MEVE, and for baseball it become h is equal to MBVB. Okay, you can substitute the formula. 6.63 times 10 to the power of negative 34 joule second. So 9.11 times 10 to the power of negative 31 kg time with the 1 times 10 to the power of 7 meter per second. Okay, so you can calculate this one. So it becomes 6.63 times 10 to the power of negative 34 divided by 9.11 times 10 to the power of negative 31 times 1 times 10 to the power of 7. Okay, so the final answer here should be 7.28 times 10 to the power of negative 11 meter. Okay, for the baseball here, 6.63 times 10 to the power of negative 34 joule second. Okay, so divide by, so the mass of basketball given 0.145 kg, and then this one is a 45 meter per second. So the value become okay, so the final answer become 1.016 times 10 to the power of negative 34 meter. Okay, so this one is due to the wavelength of the baseball. So here you can conclude that. Okay, so the wavelength of the electron, okay, should be longer compared to the wavelength of the baseball.
Okay, so this one is an application. Okay, it's due to the electron microscope. So this one is the diagram of the transmission electron microscope for viewing a flat and a thin sample here. Okay, and then here, okay, so the lenses that control the electron beam are magnetic deflection column. Okay, so this one should be your electromagnetic lens, and then this one is an electromagnetic condenser lens. Okay, so the electron microscope depend on the wave characteristics of the electrons. Okay, so microscope can only resolve details that are slightly smaller than the wavelength of the radiations used to illuminate the object. And then the electron can be accelerated to the high energies and have a small wavelength. So means that here this one coming from the formula E is equal to HF. Okay, where F here is equal to C divided by lambda. So automatic E is equal to HC divided by lambda. E and lambda is inversely proportional. Okay, so I think that's all for chapter 27. So thank you.